Hey YouTube, it's Dimitri, and today we're going to cover synthetic weight of evidence, which is a paper I just published here, I don't know, about a month or so ago. I've never seen it done in practice, but I have used it in actual practice on my teams. It's something I've just kind of came up with and used over the years. I'm not surprised that somebody else maybe has used it somewhere else or has thought about the idea itself. But I wanted to dive into this paper and give you guys kind of a hands-on practical application of how this would be used in both machine learning applications as well as specific to credit risk modeling with logistic regression. So let's dive into our drawing board here. We're going to cover, what is weight of evidence. I see it both with a lowercase o here or an uppercase O. And weight of evidence is more or less just a transformation that we're going to use to kind of clean up some of the noise around the data, which is going to be our first advantage of using this. And then the second one is going to be handling missing values. And I'm also going to put special cases because often in credit data, when we're modeling, we will have categorical variables that have been converted into numeric format. So it'll be like 1, 2, 3, and 4. And it's not actually a numerical meaning. It's just a placeholder. It could have been A, B, C, and D. And then also we have many types of missing values in bureau data as well, which are typically reviewed as like 999, which is 3 nines. There's 4 nines, 5 nines, 6 nines. They often mean like I couldn't find that customer, or I found the customer, but there was no information on this one variable, or there's truly a missing one, like, number of trade lines. Maybe they didn't have any trade lines or that specific type of trade line. So I'll have these categorical variables mixed in with actual data. So like, for example, number of trade lines is an example. Customers might have actual values like 3 trade lines, 6 trade lines, 1 trade line. And then you have a customer that has no data, missing data. They found the customer, but they don't have that type of trade line or something. And so then you'll have like a 9999. And so then you have a mix of categorical and numeric values together. So handling these special cases and missing is what weight of evidence does great at. And so just to dive in here to a little bit of the theory, these are used on binary classification sorts of examples here. So I'm going to put binary. And the example we're going to use today is going to be loans, and it's going to be probability of default, which we call PD. And so you can have a value from 0 to 1, and it's inclusive of both of these. And let's just use income as a good example of a variable here on how this kind of works and what weight of evidence is actually doing and why it's important. So on the y-axis, we're going to have PD, which is going to be actually just default, which is what we're really modeling. So I'm just going to cross that off and put default. But keep in mind, we're actually modeling the probability here. And then on the x-axis, let's say that we have something like income. And so we're going to have a 1, which is going to be the customer defaulted. And then we're going to have a 0 down here, which is the customer didn't default. And then the income itself is going to go from $0 up to, I don't know, let's say like $500,000. And what you're going to end up seeing with this is you're going to be seeing a bunch of data points that are defaulted, towards the lower income. And then the density of this is going to be high on the lower side, right? Lower income tends to default more. And then, of course, you're going to see still people like even maybe $500,000 income, and they still defaulted on some sort of loan here. But the sparsity and the density is going to change, and you might end up with some pockets here and there. And you'll have some down at the 0 as well. But you'll see this is a binary problem. And let me mark these more specifically just in purple so you can see them a little better. And so when we're modeling out these defaults here, the challenge is, right, I can't just fit a line. And if you did fit a line, it would look something like this. And that's not good, right? That's not very predictive. The model error between these is enormous. So this is not great. So we need to do something different. And so often what we'll do is we'll use a logistic function here. And we'll fit that logistic curve, and it will look something more like this. And of course, as you can see, we have amazing fit in the top, amazing fit in the bottom, and often the middle is the hardest part to fit, which makes sense even in this sort of problem here, where people that make a ton of money, right, can almost guess they're not going to default. People with no money or very little money, they're probably going to default, but the hardest people to kind of judge here is going to be this middle section here. And as I mentioned, if you had special case values, they can't fit on the chart. There's nowhere for them to go. I can't put them as a 0. That's not technically true. And if they were the 99999 numbers, they might fall in here depending where those 999s are. And if it's like so many 9 digits, you might have them way out here on the tail. And there's a bunch of issues with this. So logistic regression is just good to use in this case as it fits better. I will tell you GBM, so gradient boosting decision tree models, they worked great. So XGBoost is a really common model to use in credit modeling for PD. It does similar to this. And XGBoost is going to be doing some partitioning, which is why I'm bringing this up, is this is actually very similar to doing weight of evidence in the sense that you could partition these out, and you'd partition these and just take some sort of average here. So of course you have a few data points down here. And so the average would probably be close to here because almost all the data is up here at the top. And then again, you'd have an estimate here, and then an estimate a little bit lower. And then again, something that looks like this. And then this one's might be like, right in the middle. And then this one's going to be like way down here. Okay. And I hope you understand this from a logical business perspective here. If we were just to put a dot in each one of these groups, which is going to be the actual estimate that we had, and we ended up drawing a line here, you'll notice that line is going to be monotonic. And all this means from an explainability stance is that the business, when they think about this, the pricing and strategy teams, right, the front office development departments there, they're all getting into this. They want to understand what the model is doing. And in their mind, and in the industry as a whole, most variables have this monotonic relationship. And monotonic, it does not mean linear. And as you can see here, when we did the decision tree example, we ended up having a non-linear function, but it is monotonic in the sense that it is constantly decreasing across income. And again, it can be constantly increasing. Monotonic just meaning it has to be consistently going in one direction. So like every data point has to be the same or higher as if you have an increasing function. And in this example, it has to be the same or lower in a decreasing monotonic function. And so one issue with decision trees, again, is if we had in this case, right, 6 unique examples, that's not really granular enough. And so we would keep splitting these up into smaller and smaller groups. And of course, each leaf on this decision tree, so if you had, think about like a decision tree like this, and it keeps splitting out, the number of leaves or the number of observations inside that leaf will become too small to make a meaningful estimate here. You might have 3 or 5 or 10, and you can debate around what that estimate would be. I would argue from a industry practitioner stance, often 200 bads, which in this case is indicated by 1, should be in each leaf to get some sort of good estimate of that. Now, again, if you're working in prime, you might have a lot less just bad accounts and defaulted loans. And so this number will change depending on your estimations. And of course, the leaves that are going to be way up here won't meet that criteria unless it's too broad. There's a lot of theory and business insight to kind of weigh into this on how that process goes for fitting this. So you need to think about kind of that structure as a whole. And again, this could handle special cases with the decision tree because you could just group all of your 999s that were like way out here. You can group all these together and have some sort of estimate for that value as well. So let's just do PD again. We'll do income. All right, we'll set this chart up again now. Now, I will tell you decision trees are somewhat interesting tools because I actually use decision trees often. We build out binning tools for weight of evidence. So let me explain a little bit about weight of evidence as it will generate something very similar to that decision tree, but we're just gonna use this as a variable transformation here. So we have the same problem. We're going to do some sort of classification here. So we're going to take our data of income, and this is in dollars as we talked about, and I want to convert it to a weight or a ratio, a weight of income here, or weight of evidence of this variable itself, in the sense that we want some sort of fraction. So if we go to the paper, I show the relationship or the actual equation here in equation 2, and it's important you can look at this table below as table 2 to understand how we get what's called percentage of non-events and percentage events. When we move over, weight of evidence is assigned to a bin I, so we can have, depending how many splits we have a unique weight of evidence, and it just gets one value, just like a decision tree. And it's going to be the natural log of the percentage of non-event, which is going to be goods in our case. These are loans that are good, that did not default. And then we'll also do percentage of bads, which are those that defaulted here. Now, to think about this, what this is just imagine it as a fraction. Like I like to pretend, okay, we can ignore natural log and all that. But it's really just goods over bads. And, you know, when the number of bads is greater than goods, this is a negative value. And when goods are greater than bads, this ends up with a positive value. And so when we end up recategorizing this, we're doing the same process we talked about earlier. The only difference is when we go to partition here, so let's say we partition here, we're not taking an average, we're not using a median. We're using this weight of evidence calculation here to come up with some sort of new value. And then maybe we split it here and we have a value that's like in the middle. And then we're going to have another value, which again would be kind of like down below. So this would be like a low value, middle value, and like a high value. And so when we plot these out here, right, we have more bads up front. And so that's going to be a negative value down here. So this is 0, this is negative. So in this case, we'd have 3 data points. You'd have a negative weight of evidence. You would have some sort of middle one, which would be close to 0. And then you'd have a high one up here. And this is important because it's going to give you, again, some sort of relationship. Now, I've drawn it linear. Often it will be monotonic, just as we saw before, but it's going to be that weight of the events and non-events together that's going to give you some sort of variable here that we can use in a model itself here. So after we do all these transformations, we end up moving them into a model like logistic regression, and you can kind of contain that. You'll see, though, it is better than the raw variables because we have, you know, a lot of just sorts of different use cases, and there might be an outlier that will impact some sort of, you know, linear. So logistic regression is a type of linear regression. It'll impact that linear regression. Also in decision trees, if you have outliers as well and the leaves are getting too small, you might have unreliable data points. And so it leads us back to this chart here of income and defaults again in the example. And the whole purpose of this now is moving into what I like to call synthetic weight of evidence. And what I mean by this is often we are missing data. We have data sparsity issues here. So I have been at smaller firms, and I've even been at large firms. I've had similar problems where we just don't have enough data to make some sort of estimate. And so what ends up happening is that weight of evidence chart will often have 1 to 3 data points like this. And so then it's like, you know, for income, every customer, when it goes through the transformation now, doesn't make like $60,500, $61,000, $62,327. There's not a unique value. We kind of throw that out and we lose some of that information in that variable itself. And again, there's a trade-off between getting cleaner data with more strong relationship estimations versus getting accuracy and granularity here. And so like in this case here, if we were to split this, you can see like the density here is about the same. And then we have kind of a sparsity that's about the same in density here. And again, we don't have very many data points. So to be honest, I couldn't estimate, like in this example, if I have 5 data points, there's no way I can estimate and say, this one's about in the middle, this one is slightly closer to here, and then this one's over here. Now you can see in this example, this creates an issue. One, because now this is not monotonic. So our estimate would be here, here, and here. And so the line would look like this. And so now when you go to explain this, you would say like, okay, if somebody makes, you know, more than, let's say, I don't know, this is like 100,000. If they make more than 100,000, they're going to be more risky than somebody who makes, let's say, between like 50,000 and 100,000. It doesn't make sense. And so you can't just blindly follow data because you have data here. So data sparsity is one of these issues where if you just don't have a lot of observations in general, you're going to only be able to estimate maybe 3 data points or 2 data points. And I've had many variables where there's just 2 data points. There's like missing special cases and there's everybody else. And sometimes that logically makes sense, but a lot of times it doesn't. So sparsity is going to be our first kind of thing we're going to point out here. And the second one is going to be kind of clustering, and clustering mixed with sparsity is often an issue here. So imagine that you had like 90% of your data in this region here. So you could really reliably estimate this sort of data point within itself. But the issue is the last 10% covers this. So what I'm saying is I can estimate anyone with an income of less than 50,000 extremely well, but I have no possible way of assigning a weight of evidence value reliably, right? The estimate of that is not going to be good. Now, when I say synthetic weight of evidence, I do not mean we synthesize new data points and add in a bunch of data points down here so that we can estimate that. The reason I don't like that approach is because often when you go to this one, you have to either assume a distribution, which I don't like doing. There is fraught with issues with that. Estimating that distribution, determining that distribution is a whole challenge in itself. The other approach is using historical simulation and randomly selecting and drawing from that pool that you have. I also think this is really poorly done, because if you sample enough and it is truly random, you will just take your small population and make the exact same population, but just bigger. So if you had like 10 unique values, you're just gonna have the same 10 unique values, but a lot of them. Unless you come up again with a distribution, maybe use kernel density estimation. You can see this is getting a little bit too complicated for what we're trying to do here. Let's keep it simple, and let's realize the goal here isn't to generate more data, just to generate more data, then to solve the problem of estimation. The goal here is, how do we just get a reliable relationship? Because we're trying to estimate a relationship. So you could generate a bunch of data, fake data, synthetic data, then you could go through and estimate that, and you have an issue perhaps in the way that you pick the estimation procedure. And then finally, you're trying to get to the actual relationship, which is this line here, which we're using in weight of evidence, right? So the way around this is I've basically just splice and fit dots in the middle. And I know this sounds really stupid, but it makes a lot of sense here. So like in the example of income, as we talked about, if I had, 500,000 over here and I have 0 over here, and I said, this is the relationship, the business would say this completely makes sense, right? A lot more income means they're going to default significantly less, and a lot less income means they're going to default significantly more. They can also start to justify things like slope of this line. So again, going from like 30,000 to 50,000, which is a $20,000 gap, you would expect the probability of default to significantly decline. So when we transform this into weight of evidence, you remember that negative values are going to be more bads, and there's going to be more goods on top. You would assume it's not going to be linear. It's going to be like, more money, like an extra $10,000 for someone less than 100,000 is probably gonna make a bigger difference in that probability of default, right? It's gonna make a big impact. But if you go from making like 400,000 to 410,000, I don't think it's going to move the needle very much here on defaults, because you already have a bunch of excess capital. There's really not an issue. You could shuffle some things around, move some accounts, and do something about it here. So we would expect to see, again, this shape be steep at the beginning and that curve flatten off towards the end. Now, if we had sparse data, and I want more than 3 values here, and the reason I want more than 3 weighted evidence values is I want more granular predictions, right? In this case, anybody from 100,000 to that 500,000 mark is going to get 1 value. So let's just say, it's like 1.3. And then the value from 50,000 to 100,000 is like 0.1. Okay. And then your weight of evidence value from $0 to 50,000 is like negative 3.6. Again, we're only going to get 3 unique values for every customer. It's not great granularity. I want better accuracy in the model. To do that, I'm going to have to bring in a bunch of other variables as well. But also, I'm not really getting the true information out of this variable. We have oversimplified it, and we've thrown out too much true information about that consumer here. And now weight of evidence, though it can handle the missing case values, and though it's simplifying this, we've oversimplified. So the way to do this when we don't have the data is just using what I call synthetic weight of evidence. And that's just really taking the 2 data points and splitting them in half. So taking income here between 100,000 and 500,000, we could split this and say, this is going to be the new spot, which is going to be 300,000. We'll just split it in half. And now we will use the original data point, which we had, which was here. And we're going to just split those two into 2 parts. So if you look on the right hand side here, we're going to split this in half, and we're just going to put a new data point here. We're not going to use any of the actual data to do the estimation here. We're just going to take the weight of evidence value here and the weight of evidence value here, and we're going to split it in half. So we'll add them together, divide by 2, and we'll come up with the new weight of evidence value. This is a way of just doing a simple assumption of equal weighting to get a very simple approach here. So I'll tell you, for synthetic weighted evidence, there are multiple ways you can do this. A simple average can be done to split these. The second one is you can use nonlinear estimation or curve fitting. And the third one is using something with weighted. And so doing the simple one, right, you could just add in 2 more data points here and here, and you could end up having more granularity such that you would have, a dot here, a dot here. Let's hope a dot like somewhere probably here. And then these dots would hopefully be properly estimated and be closer to down here. And so you'd end up with a much, much more reliable estimate, curve, shape, and design. Again, this only works if you can estimate a proper curve, justify the original curve that we had over here, right here. If you can properly estimate that curve, and then you can add the synthetic data points in the middle here. Now, simple weighted average, to be honest with you guys, it's worked great. It has worked amazing. We've used it in practice. We built out a model, standard weight of evidence, went out, built the model, checked the AUC, which is what we were using for this. And we had okay. We're like 71. Went back, did some synthetic weight of evidence, got up to like 75, which is a pretty big jump, 75, 76, just by changing these sorts of weight of evidences here. So it's just trying to create more granularity in that framework. Now, as I mentioned, right, this is just overly simplistic, but it does maintain the explainability, right? The monotonic relationship. This is stellar if you put this into something that's nonlinear like a decision tree, because it forces the relationships to be simple. It forces the values to have this monotonic relationship. If you have a decision tree and you end up making splits on this, and you end up capturing, for example, like a split like right here, and all of a sudden you just have one or two data points, there's too few in there, you're gonna get a bad estimate. So you'll have one here, and I'll show you here in the paper in a second, this granularity trade-off, but essentially you'll get bad estimates from this. So being able to estimate on a much larger population, get stable estimates, and then create synthetic data points in the middle is critical. One last thing before I jump to the charts in the paper, is going to just be like, you could use a cubic spline if you wanted. Instead of just splitting these lines in half as I'm doing over here, you could have a dot that perhaps is like a little bit higher here, and it might be a little bit higher here as well. Maybe you have more of a curvature to it when it's connecting these dots. You could use cubic splines, polynomials. I have a video on polynomials, which maybe I'll put above, I don't know, maybe I'll put in the description, on fitting polynomials in Python. You could use that to get more of a curvature, and that might actually get you more accuracy. It maintains the explainability piece here. The other portion of this is you can still rely on your data and use weights. So instead of just assuming, as I split, like with this line right here, where I split this in half, and just assuming it's half and half, I might look and say this is like 65% of the data in this range right here from 100,000 to 500,000. And this is gonna be 35% over here. And you could do a weighting of the two dots themselves when you do the split. So in this case, we have a dot, we need to do some sort of splitting within these different regions. Again, you're going to be splitting, you'll have different partitions depending on where you're doing it. So maybe this is 35%. And so when you go to do the splitting of this, in this case, you're going to be looking at, just a weighted approach to doing this. So adding the two numbers together. So in this example, you have a number here for this dot, and then you had a number here for this dot. You add them together, and then you create the sort of split itself and do a weighting process to that here. So I know this isn't mathematically like, I'm going to sit and go through all the details on exactly how this is done, but I hope this is a good intuition of like how we're taking this final weight of evidence transformation, splitting the dots, and then just assigning those new values there. And so here's an example in the paper itself, right? Showing a variable beforehand with 5 bends, and then splitting it down into further bends where we added just 2 more in here. I get a little bit more into the details of like, sometimes you just can't split, or you shouldn't split, or there aren't true values in those regions. So if it's categorical, right, you can only split down to the number of categories. It makes no sense to have like a new magical category when no value is gonna come in at that point. And I did provide some examples here of some real data just to show you kind of some underbending and overbending. This applies both to decision trees as well as weight of evidence. You can see like the first chart here on the left, we have underbending. We have 3 data points. In my mind, it looks really sharp. The slopes are odd. This makes no sense. And then when we look like at the far right, it's like we have this weird spike at the top. And so in my mind, I'm starting to like justify this, right? Like the first data point must be like a missing value maybe. And then we have this spike, and this relationship's a little odd. Also in variable 1 here with this little red circle in the paper, I believe I had sparse data in this pocket, and so I couldn't estimate it quite right. But that group performed very differently, so I wanted to model that. Again, having that non-monotonic piece there creates a little bit of a logical issue and fallacy of like, is that a true relationship, or is that just an issue with the data here, right? The sampling, the approach, the customers, the business strategy that had the sampling different. And also you can see here, like in variable 3, or I guess variable 4 here, which is figure 7, these charts right here, you have a nice monotonic relationship here. And as we add granularity to it, you can see we start to end up out here in the right tail, and you end up with these bounces. That's because we have sparse data in that right tail. Whatever actual variable this was, there was obviously more data in the lower values here. And so when we ended up estimating those, they move a little bit, but there's not a lot. But we would like to smooth that out and have some sort of logical relationship for that. You don't want to let your data itself just drive the estimates. You're trying to build in an explainable, logical framework here. And as I mentioned, this is great for machine learning, XGBoost models. It helps get reliable results that when you interpret the results at the end and the business sees them, they understand them, they'll have good buy-in because they can look at the weight of evidence charts, they can look at the results from these sorts of models and understand how they work well, and how they are explainable and the relationships have some sort of direction to them. Anyways, that's synthetic weight of evidence. It's really just doing weight of evidence and then adding synthetic points in the middle here. Again, looking at kind of simple averages versus nonlinear estimates versus kind of weighted estimates. There's a variety of ways you can kind of create those points in the middle. Yes, it is very simple, but surprisingly it works well in practice and helps increase granularity in the predictions without sacrificing kind of crazy unreliable estimates in the model itself. So I hope you guys enjoyed this video and found this helpful. If you'd like more information on this and more details and examples and kind of the layout of how it's done, I'd encourage you guys to go take a look at the paper itself, and I'll put a link in the description to the paper. Thank you for watching, thank you for listening, and as always, until next time.